speaker, Professor Martin Savage, who is a prominent theoretical physicist and one of the leaders of the newly emergent hot area of scientific quantum computing. So Martin started his education in Auckland, in the beautiful North Island of New Zealand. He then received his PhD at Caltech in 1990, working on heavy quarks, did postdocs at Rutgers and UC San Diego, and already in 93 became assistant professor at Carnegie Mellon, from where in 96 he came to University of Washington, where he stayed ever since, and where he is a professor and senior fellow at Institute for Nuclear Theory, and where he now also directs the incubator for quantum simulations. So Martin will tell us today about quantum computing in nuclear physics. So Martin, please take it away.
Yeah, thank you very much, Dima, for the introduction. Let me share my slides. So I modified the title a little bit from the default that, and I'm going to talk about some of our recent progress. I decided that seeing this was a seminar, it would be an opportunity to tell you about some things that are not published yet that we're working on. So let me do this. So yeah, thank you very much for the introduction. So I'm going to tell you about some of our recent work that we've been doing in 3 or 4 areas related to quantum simulation, particularly digital quantum simulation for nuclear physics. This work, of course, is made possible by collaboration with outstanding junior scientists spanning from research assistant professors through to undergraduates. The first 2 works that I'll tell you about is progress we've made in 1+1 dimensional QCD, and also looking to explore some real-time dynamics, as one would see in the lab, in this case, beta decay. This is work done with graduate students Roland Farrell, Nikita Zelimsky, and Ivan Chernishev, postdoc Mark Iller, and undergraduate Sarah Powell. I'll then tell you about some very recent work with Mark Iller related to entanglement in dense systems of neutrinos, particularly coherent evolution as relevant for evolution of a supernova. And then finally, I'll tell you about some work I've been doing with Caroline Robin recently. This work's not on the archive yet, on Hamiltonian-Learning and VQE for effective model space in the Lipkin model.
What is VQE?
Variational quantum eigensolver. So I'll explain when we get there how that works. So chapter 1. So there's two papers that we've written here. One on setting up 1+1 dimensional QCD, and of course this builds on extensive work by others over a period of time. And then we're able to also prepare within that framework a baryon, a single baryon, and then we introduce weak operators and then watch for it to beta decay. Of course, the phenomenology is very different in a small system on a 1D lattice to the real world, but it's something that will converge as one takes continuum limits and increases the number of dimensions and so forth. And it's really about developing algorithms and understanding about how to do such processes. So this was stood up on the work by Christine Mushik, Randy Lewis, and others et al. From early last year, where they set up and prepared issue 2, 1+1 dimensional lattice gauge theory. And of course, that was built upon extensive work, including by members of the audience here, on 1+1 dimensional quantum electrodynamics. And after our first paper on 1+1 DQCD, within a couple of days, a paper appeared, and we actually talked to them, of course, by Christine, Randy, again, and et al., where they also looked at issue 3 in 1+1 dimensions. I should say that this work was supported with quantum resources from Oak Ridge, from the Quantum Science Center, and we made use of the IBM Q devices and the Quantinuum 20 qubit trapped ion quantum computer. So one of the motivations for us to explore these types of processes, if you like, go back to the early 1980s in chemistry, where there was a real revolution happened with short pulse lasers, where one could actually prepare a particular system or particular reaction and then use lasers again through diffractive scattering to look at the evolution of the electron density and map out the reaction pathway. Now, we don't have that luxury in nuclear physics or high energy physics, but we do have the ability, at least we're working towards developing the ability so at some point in the future we can do time evolution in a simulation. And so we would like to understand or take this type of technology that was developed to look at chemical reactions to see what we could learn then about nuclear reaction and high energy reaction pathways in terms of the behaviors of quarks and gluons. And so this is what prompted the second work here on beta decay, to see whether we could look and see the behavior of entanglement, and particularly between the quarks and gluons and the modifications to the densities of quarks and gluons during the reaction, the simple beta decay reaction. So just a reminder about QCD, I don't really need to tell anybody in this audience what quantum chromodynamics is, but there's a couple of features here that are relevant for quantum simulation, so I will. So the Lagrange density for QCD is very simple to write down. There's a kinetic energy term for the quarks, which contains both a partial derivative acting on the quark field and also couplings to the gauge field. There's a mass term for the quarks, and then there's the kinetic energy and potential energy in the gluon field in terms of E squared and B squared. So this is entirely the QCD Lagrangian, and is what we've been focused on since the early 1970s. Now, when it comes to and of course, there's been enormous progress in using classical computation through Lattice QCD and other techniques to evaluate aspects, low energy observables primarily related to QCD, and matrix elements of forward matrix elements and nucleons and nuclei and so forth. When it comes to quantum simulation, one works in the Hamiltonian formulation, and there's a well-known and then some lesser known formulations of the Hamiltonian, as we'll come to later on. But you see there's really two different types of fields here. There's the quarks, which are fermions, and then there's the gluons, which are bosons. And so when it comes to simulation on a quantum device, with again, any computational platform with finite resources, one can only work with discretized and digitized but then the boson degrees of freedom will have to be digitized in their own way. And so one of the efforts that's going on at the moment is to understand how to optimally deal with gauge fields on quantum devices. And I'm really not going to say much about that. But the point is that one has to deal with two different species of subatomic particles, map onto qubits, and then perform operations on them. So from a digital quantum simulation point of view, there are just a few things that we have to do in order to go from the beginning to end, but each of them presents enormous challenges, and we're really only just starting down that path. So as I mentioned, the first thing we have to do is to understand how do we map the quarks and gluons onto quantum registers of qubits or discrete Hilbert spaces. The discussion is different when it comes to analog simulation, slightly different, but I'm really going to be focused here on digital simulation. And so for fermions, it's one can straightforwardly understand how one can map fermions onto discrete Hilbert spaces. When it comes to the gluons, of course, then there has to be a local register where the continuous degrees of freedom are then digitized onto, there's going to be a cutoff, say maximum value of the field, minimum value of the field, or the dimensionality of the irreducible representations of the SUN group, something like that, that tells you how to map the field onto a finite Hilbert space and then control it. And so at the moment, we're still understanding those digitizations, the effects of the cutoffs and so forth. There's work on scalar field theory during the last decade by Jordan Lee Preskill that was remarkable work. It really defines the gold standard for quantum simulation of field theories that showed how to, at least in the case of the scalar field, efficiently map onto registers of qubits, and showed how to, at least in principle, laid out the framework for performing scattering experiments as you would in the laboratory. And of course, when it comes to QCD, we want to go down that path also. It's complicated by the fact that initial and final states are composites of the quarks and gluons, and it's the quarks and gluons that one is going to be defining the quantum simulation in terms of. So the first challenge that we have in quantum chromodynamics is understanding how to prepare the initial state, not just the vacuum state, but then on top of the vacuum wave packets of, say, protons, or preparing a nucleus or something like that. And as I said, the very first steps are moving in that direction, but we're very far from accomplishing that. And so then after you prepared the initial state that you would like, then one then has to evolve it forward in time. One can evolve it forward in time with unitary operations acting on the quark and gluon fields. And so quantum circuits need to be developed that can systematically evolve the quark and gluon fields forward in time under the dynamics of the QCD Lagrangian. Of color charge, and so one has to somehow ensure, and I'll come back to this later on, that Gauss's law is satisfied, and so the color fluxes coming into vertex is the same as the color fluxes going out of vertices when one can takes into account all of the fields, the quarks and the gluons. So developing the unitary operators is also a challenge. The next part, which is also a challenge, is the measurement and the error correction and all of those things. Those are somewhat more generic to quantum simulations in general, so I'm not going to talk about those too much. The one exception to that is, how does one actually make measurements and define scattering cross sections? You know, how do you know when you have protons going into some volume of your simulation? So that's also something that was discussed in the context of scalar field theory that is an active area of investigation. So Yang-Mills in higher dimensions, because I'm really going to be focused on 1+1 here, but let me make some comments on higher dimension. So the Kogut-Susskind Hamiltonian is how one is the Hamiltonian. One can construct your links in terms of the electric fluxes. There's in that basis, there's a contribution that's diagonal from the E-squared operator, and then there's also contributions from plaquette operators that determine the contribution, the magnetic contribution. And in the electric basis, one has set up the Hilbert spaces in terms of the dimensionality and also the orientations, the dimensionality of the color irrep, but also the orientations in the left-handed space at the tail of the vector and the right-handed space in terms of the tip of the vector. And so the dimensionality is common. And so as you see here, where my cursor is, the typical state, linked state, is denoted by a pile of numbers. So P and Q define the number of upper and lower indices of the issue 3 tensor. So for instance, for a six representation, P is 2 and Q is 0. Then one has the color isospin orientations and the color hypercharge orientations on the left side, and the color isospin and color hypercharge on the right side. And of course, the plaquette operator is a closed loop that's gauge invariant that you can form from 4 links, at least in its minimal in its minimal form, and the electric is just the Casimir. So when we go to 1+1 dimensions, there's been, as I mentioned before, there's been extensive work on understanding the Schwinger model since the Schwinger model was discovered. When the era of quantum simulation, of course, the Schwinger model provides a really interesting sandbox for both theorists and QIS people to really make progress in and understand in detail. And as many of the algorithms that will be needed to analyze the Schwinger model will also then go on and be used in QCD in both 1 dimension and higher dimensions. 1 dimensions is special in the sense that the gauge field is completely constrained by the charges on the lattice sites. And so there's no dynamical gauge field, which makes it obviously only just part of the story. So even if we understand the Schwinger model and the non-abelian 1+1 dimensional theories, then that only takes us part of the way towards understanding how to do QCD in high dimensions. In particular, there's no plaquette operators. One of the fortunate things is that in the quark discretization in one dimension, the staggered discretization, the continuum limit of the staggered discretization gives you a single fermion in 1 dimension. It doesn't have doublers associated with it, which makes it a faithful mapping. And so the Jordan-Wigner mapping of the fermion field works just fine in 1+1 dimension. And even though there's other mappings, that's what I'm going to be talking about here. And so if you think about what we need to do here for QCD, and in particular, we've started focusing, this work is on multi-flavor issue 3 or higher. And it is different from issue 2 in a way that was somewhat surprising, but you can't just take issue 2 and then move to issue 3. And so what we have here is that for each spatial site, there's 2 fermion sites, one associated with the quark and with the anti-quark. For each color, there's a site, and for each flavor, there's also then replications of those 3 sites. So the remaining thing here is to define the gauge. And so there's a couple of options that you have. One can work in the gauge where there's no plaquette, there's no link operator in the time direction, in which case one has then link operators in the spatial direction. So this is A0 = 0 Vol gauge. And so one then has degrees of freedom for the fermions and for the gauge field that is constrained, of course, by Gauss's law. And the Hamiltonian that you write down for Kogut-Susskind has the following form of a kinetic term with interactions with the gauge field. Here, there's a mass term, and then there's the contributions from the chromoelectric, where these correspond to the actions of the Casimir on Hilbert spaces denoted on the link. So here, of course, you can map, the fermions map directly onto spin half systems, but then one needs registers for the gauge field. On the other hand, there's other gauges, right? And we know that choice of gauge can make your life simpler or harder. If you work with axial gauge, it turns out, and this can be arrived at from Vol gauge by a simple unitary transformation that was shown by Serac and Banyuls and others. Then the Hamiltonian has a different form. There's a kinetic term, but there's no coupling to the gauge field. There's a mass term, and then there's a non-local contribution from the interactions of the charges. So it looks like a Coulomb term, but it's complicated, more complicated because it's a gauge field. But you can find this construction in any lattice field theory book. For quantum electrodynamics, the charge operators, of course, just provide a phase to the state, whereas for non-abelian theory, the charge operators can change the color. They can leave you in the same one, but there's also amplitudes for instance, changing a red up quark into a blue up quark. And so the evaluation of this term is in fact the one that takes all of the quantum resources in a simulation. So the mapping then, to be more explicit, if you just focus here on the left-hand side. So for instance, the first lattice site has 2 flavors in this example and 3 colors. And so that turns into a requirement of 6 qubits. So one has the up red, up green, up blue, down red, down green, down blue. and then there's the anti-quark partners. And so to define one spatial site of lattice QCD here, one spatial site of QCD requires 12 qubits. And so as an example, so the antiferromagnetic vacuum state when determined by the mass term, when the kinetic term's off and so forth, is just simply all followed by all spin-ups. So it's again just a generalization of the Schwinger model. The Hamiltonian is more complicated, of course, because as you see, the kinetic term, which couples, for instance, uprids with anti-uprids, has operators now that are separated by a number of qubits determined by the other colors and the other flavors. The mass quark is fairly standard. It's a local operator and just looked at the orientation of the quark over each of the flavors and each of the colors. And then the contribution to the energy of the E² term, the charge-charge interaction, is complicated and involves, as I said, a non-local sum. And one can, the real setup here, one can think of the simulation as a physical picture. As you start here on the right-hand side with 0 electric field entering the system, and then if there's a quark present, then this introduces a red component into the introduce a red component, then you go over here, introduces a green component, introduces a blue component. And by the time you get over here, there's a first contribution to E² is from here. You've had to coherently sum all of the charge contributions from all of the 3 colors of the up and down, and then you square it and you ask, what is E² here? And then you continue your path. So Gauss's law, you add all of these contributions together. So by the time you get over here, in principle, depending on what the color structure of the lattice is, one could in principle have a large E² coming out of the other end of the lattice. And I'll come back to that later on. Well, so yeah, so we're working with open boundary conditions, starting with E initially, and then potentially a non-zero E coming out this side. And I'm going to say more about this. But the point is here, these open boundary conditions support color edge states. So the total cost to this Hamiltonian for having, for instance, a blue anti-down quark, for instance, here is very minimal, right? Because it just, if everything else is color neutral till you get to this point, and then you have an excitation here, then it's a low energy excitation unless you penalize it. Because the cost of having E² out here is just related to the coupling G². So one of the things that we did was to put in a penalty term for having non-zero color electric field beyond the end of the lattice by adding an extra contribution of this form down here. We called it H1 to force everything on the lattice to be a color singlet. And I'll show you, and so so this eliminates the edge states. So if you look at the spectrum here of just one site and one spatial site, so this is just 12 qubit systems, and you ask, what is the spin, what is the color structure and the flavor structure of this of the low-lying spectrum? Then when all the couplings are 0, you have an SU12 symmetry. When you turn on the strong coupling G², one sees splittings between these levels that you can identify completely, basically with states that reside in the bulk, but also color edge states. And that becomes clearer and clearer as you crank up the coupling G², and you see states here that don't really vary much with regard to G², and this is an edge state. These are edge states, and these are where the physical color singlet states lie, the lowest lying ones. And here, as you can see it in the spectrum over here, as you start turning on H², the penalty for having a color non-singlet state beyond the edge of the lattice, you see you just have the color singlet states remaining in your spectrum, and you see the edge states then become increasingly high energy. So the Hamiltonian, of course, for a classical simulation, you can take the system and just diagonalize it on a very big classical computer. And I say that in principle, of course, this becomes challenging rapidly. That's why we're all here. If you look for this particular system with one lattice site, 12 qubits, then the matrix size, after you've projected down onto the relevant sectors, you're dealing with matrices of order 88 by 88. But as soon as you get a 3 sites mapped onto 36 qubits, you're looking at a matrix of 200 million by 200 million. And so you see that this gets out of hand very quickly, and you can only imagine the resources required to do, say, 100 100 lattice sites. So for what we're going to be doing later on with weak decays, then we need to look at the baryon spectrum and the structure of one-dimensional QCD. The systems don't, the fermions don't have spin, but there is still some resemblance to what we know from the lattice spectrum of QCD. So there's meson states, isospin 0, isospin 1, the sigma and the pion. And then there's the lattice baryon state, which is isospin 3/2. One doesn't have the luxury of performing the mixed symmetry state to get the nucleon, but you do have the isospin 3/2 delta present as the lattice baryon. But you also have a bound state. It turns out that the delta I equals 0 object, the 2 baryon state, is also bound. So you do have a deuteron, and I'm using air quotes here. One does have a deuteron in the system that we can work with. So one can actually start to do some deuteron physics in principle with this type of system. Also, because it's isospin 3/2, one can then introduce isospin breaking through the quark masses, but also one could think about including electromagnetism if you wanted to do that. Or you could include chemical potentials for the flavors to split the baryons. And we used the former, so we introduced different masses for the up and down quarks to split the delta 3/2 multiplet to allow us to study beta decay between members of the multiplet. So one of the things that, of course, is popular that we were thinking about here is looking at the mass decomposition of the states in 1+1 DQCD. Many of you have worked on this, and it's really interesting. And there's a period of confusion that has luckily passed when it comes to what's observable and what's not observable, and so on. So in this particular system, we have a Hamiltonian. We can decompose it into kinetic terms, mass terms, glue, in axial gauge. And so these are all perfectly well-defined quantities in axial gauge that we can evaluate once we know what the wave function is on the quantum device. So we looked at these for single baryons, but we were able to look at the deuteron and then look at what is the contributions from each of these elements in the Hamiltonian to the deuteron binding by taking appropriate correlated differences between matrix elements and the wave function. And so if you look at what is contributing to the deuteron binding, then you see that the mass term contributes a negative amount, which seems a little odd at first, but it's totally fine when you're taking differences. The kinetic term is contributing, has the biggest contribution, and of course the kinetic term is an operator that can create QQ bar pairs. So in some sense, the deuteron binding is dominated, the contributions to the deuteron binding energy is dominated by the presence of QQ bar pairs, which in a hand waving point of view looks like mesons, of course. The gluonic contribution is quite small. And so this is the total binding. You add the blue, the green, and the yellow, and you get the red. So because you have the states, you can also look at entanglement structures in the meson. So this was another one of the reasons that we were interested in exploring the system. And so in this particular instance, one can look at the entanglement between quarks and antiquarks in this system as a function of the coupling constants. Sorry, and so what one finds is some interesting structures here. So what's shown here, upper left, is the entanglement, the linear entanglement entropy as a function of the strong coupling G for the pion. So this is the isis triplet state. And you see variations of order 10%, but there's definite patterns where above a bit there's an inflection, a G of order 2, and then a maximum value at 2.4 something, and then a fall off. And if you look at what that corresponds to with quark occupation, something that you can pull directly out of the wave function, then you find that there's non-trivial structure in the occupation. And at this inflection point, the maximum of the linear entropy, this is when the quark occupation makes a jump. And so what's going on here is the structure of the state is changing from something that is intrinsically QQ bar dominated. So it looks like a quark and antiquark as the interpolating field for this meson, transitions to its strong coupling to being a baryon anti-baryon. pair. So there's really a structural change in this state as the strong coupling sweeps between 2 and 3. That is signified in the entanglement entropy. So the entanglement entropy is a maximum when in fact this configuration is transitioning from QQ to baryon antibaryon. So the entanglement entropy is actually revealing about the actual structure of the state. So one of the things that we were confused about actually for a while here is the fact that naive trotterization breaks issue 3. So if you trotterize the energy in the electric field and apply it to your state with unitary time evolution, then in U1 and SU2, then you can trotterize and you will not break U1 of electromagnetism, and you will actually not break SU2. But in the case of SU3, you actually introduce non-zero trotter errors because of the non-trivial non-commutivity of the charge operators. So in particular, you find you can group terms together into groups of commuting operators, which then you can discretize. But you find, for instance, the action of the unitary of charge 6 up, charge 6 down, plus charge 7 up, charge 7 down changes the actual charge, the up plus down charge of the A equals 1 generator. So so this is a new element when it comes to dealing with issue 3 that we're going to have to deal with when addressing QCD itself. So there was a couple of ways that we went about dealing with this that we explored. They worked as expected. They worked okay. So for instance, one can perform a trotter step and then do a random reorientation in gauge space. So for each member of the ensemble that you simulate, and so on average, this will eliminate the color non-singlet contributions. So this is a stochastic sampling. So this, we didn't explore the details of this too much. This certainly has to be explored further to understand the convergence of that. It's known that this type of resampling will mitigate gauge errors, but the question is, how effective is it? It's effective at some level. The question is it effective enough? The other thing that we looked at was actually introducing an improved Hamiltonian, so introducing terms into the Hamiltonian that we then simulate to exactly cancel the leading order contributions induced by this trotterization, the violations of color induced by this transformation, and that was actually quite successful. And so this Hamiltonian improvement program, analogous, for instance, in Lattice QCD to the semantic action program and other improvement programs, seems that we'll actually have to implement this for issue 3 simulations to deal with color, potentially color violations. So to show you that we actually did some non-trivial work here, we constructed quantum circuits for each of the elements in the Hamiltonian. We used the GHZ representation where you can simultaneously diagonalize a number of the terms. And we're able to group together, for instance, the 4-body operators resulting from the charge-charge interactions together with some Z rotations and some diagonal ZZ and Z. We relied heavily actually on some of the techniques that are developed in quantum chemistry to reduce the number of entangling gates down to a minimum value.
I'm sorry, Martin. So there is a question in the chat. So people are asking about trotterization. So they are not familiar with the term.
Oh, I'm sorry. Yes. Okay. So trotterization, what does this mean? So one wants to have a nice unitary operation on your, so you have prepare some initial state, for example, and then you want to time evolve it forward with e to the negative I ht. So typically for a given Hamiltonian, one doesn't understand how, one can't construct the quantum circuit that explicitly implements that unitary. However, the Hamiltonian can be broken up into terms generally, and then individual subterms, then one can construct the quantum circuit efficiently. Again, it's about efficient preparation. In principle, one, of course, can construct the quantum circuit. The question is, can you actually do it in reality? So by breaking the Hamiltonian up into terms that are manageable, then one can arrive at quantum circuits to apply sequentially. And so the point is, as you break it up and apply unitary 1, unitary 2, unitary 3, then first order, of course, gives you the action of the sum of the Hamiltonians times t, but there's discretization errors. In particular, if the terms in the Hamiltonian don't commute, then you will find contributions that you didn't want. And so they vanish, they can be shown to vanish as the time step goes to 0. But for any finite time step, then you in general did that answer your question?
Thank you, Martin.
Okay, great, thank you. Yeah, sorry for not explaining earlier. So we actually did simulations here on IBM devices. We used Perth and Jakarta, the 7-qubit systems, to look at one flavor, one lattice site, 3 colors. So this is basically the bare minimum object that you can do in issue 3. We were somewhat pessimistic going in, given the size, the depths of the circuits across 6 qubits. Number of error mitigation techniques that have been developed over the last period, which have turned out to be remarkably effective. And so what we're really talking about here is one trotter step requires the application of 34 C-naughts per trotter step. And the techniques that we use to obtain results, we use dynamic decoupling, where this was developed by IBM, where when you're applying your quantum circuit to a few qubits and others are sitting idle, you actually flip them to deal with some residual charge effects on the chip. Another one is the C-naught gates are not perfect. So when you apply a C-naught gate where you have a control versus an X operation, the actual application of the control actually twists the qubit. It's not perfect projector, and the X operation is not a perfect operation. And so to compensate for this, you can turn that coherent error into a statistical error by using Pauli twirling. So basically, every time you have a C-naught, you reorient with Pauli's on the 2 qubits and then unreorient, if you like, after the action of the C-naught. And you do that in a statistical way for every C-naught in your circuit. So we ran 447 Pauli twirled circuits for each nominal ensemble, for each element of the ensemble. And we ran 1,000 shots per circuit. So we did it 1,000 times. And we also then employed post-selection, where we only took physically relevant states, because if you have an error, and there's lots of errors, if you have an error, it takes you out of the physical space, then you can just eliminate that and normalize your ensemble size. We also use the new technique, the decoherence renormalization, where one has a quantum circuit that you want to act on your initial state, but the system is decohering by the action of the circuit and just by itself. And so you can run the same circuit, but with, say, 0 angles, and that should leave the system unchanged, but it won't. It's going to give rise to an exponential decay toward the classical decohered configuration of the device. And so that gives you a measure of the decoherence, which you can then renormalize out. And that was really important. And so in this calculation, then when you use all of these error mitigation strategies, you find this curve here on the left, and you find these are the results from the IBM devices, Perth and Jakarta. And you see that these are high precision results that reproduce well the dash line, which is theoretical expectation. So from just even a year or so ago, 18 months ago, where the error bars on these calculations would have been quite visible and quite large, these mitigation techniques allow us to actually now recover precision results on the IBM devices for non-trivial quantum circuits. And in this case, it's a 34 C-naught circuit. We have recovered also significant, meaningful signals on something on a circuit with 400 C-naughts on it, as have others. Others have run, particularly the Berkeley group, Christian Bauer and Ben Nachman collaborators, and the group at York University, Randy Lewis and Sarah Powell, they were the first ones to implement this type of error mitigation, and it works incredibly well. So if you look at the number of CNOTs required now as we go to larger systems for issue 3, so this is what we ran one site for one flavor, it's about 30 CNOTs. I said 34 up here, but you can take a liberty on the final sequence to drop 4. If you then increase to 2 flavors, this goes to 114. And now if you go to 10 lattice sites, which is sort of now minimal for getting into doing calculations where you can attempt to have localized states and volumes that are large compared to the intrinsic scale of the strong interactions. With 2 flavors, you're looking at about 34,000 CNOTs per trotter step. And for L equals 100, it's about 3.5 million. So non-trivial numbers of CNOTs, we are not able at the moment to run anything really. We can start to run L equals 2 one flavor and expect to get results that have meaning to them and meaningful error bars. So this was just mentioning the post-selection and Pauli twirling, which I've told you, and giving you references to look at. So I'll skip this. So what am I doing on time here? Oh yeah. So the Pauli twirling and mitigation.
Sorry, Martin, there is another question.
Oh yeah, sure.
The question is it really negative probability for t equals 2 and 3, or is it just for the visualization?
Oh, so here, so this is just this is a fact that we've done extrapolations here that were not perfect. Mm-hmm. So this is just an artifact. This is just an artifact of what we've done to process the data. The results that came off the device were not negative in any way. They're all positive, but they were sitting up here somewhere. And then we had to extrapolate from the decoherence value through the renormalization, the decoherence renormalization of that other circuit, which is again a statistical evaluation, and then extrapolate. So the fact that these are different is entirely a systematic of the fact that we didn't do a complete error estimate and subtraction here.
Great, thanks.
Yep, sure. What happened here? Oh, there we go. Yeah, so some comments here on the twirling and mitigation. And so this is so the Pauli twirling. So basically, you have a particular quantum circuit. It has some parameters, and then for each C0, you randomly select how you're going to orient the C0 through Pauli twirling, and then you do its exact inverse to unmap it, and then you do this for all the C0s in the circuit. So you have, every time you're running a Pauli twirl circuit, you have a different circuit that you're actually running through the device that samples a different aspect of the systematic errors associated with imperfect C0 gates. And so in particular, for instance, here, if we take the circuit, the blue circuit here, for instance, t equals 1, then this is the results of the circuit running that you get off the device. So you see, you don't just get one value because you have non-trivial systematics associated with C0, you get a distribution. So this is on Perth and this is on Jakarta. So you actually see that the distribution, the C0 gates are actually a little bit better on Jakarta than they are on Perth for these circuits. And so then for the physics mitigation circuit, so this was to remove to perform the decoherence renormalization, then again, these should all be 1 in an ideal world. They should all be sitting here. But you see that there's a non-trivial distribution that's different for both devices. And notice that these are log scales, so it's not as bad as it actually looks. But nonetheless, you see that there's a lot of information depending on a lot of information encapsulated that you can uncover and unfold by looking at how the distribution of the ensemble under twirling. And you'll also notice there that if you're pulling off an amplitude that's small, so you've done a time evolution that's taken you from one probability of order 1 to probability of order 0, you see that the distributions are quite. So I don't think we've extracted all of the utility of this method yet, but we're looking at it. But I think this is kind of wide open to see how we can further extract information. So the weak decays, and this is, and I'm going longer than I thought I would. So the effective operators for beta decay is a 4 Fermi interaction where, for instance, you have a down quark transitions through the V minus A interaction to an up quark and then produces an electron and antineutrino. And so we have the operator here. There's the Fermi constant sitting out the front divided by √2. There's the CKM matrix element VUD. There's the spinors. And then, of course, there's Hermitian conjugate. So this is what nature looks like. For the 1+1 dimensional simulation, of course, we don't have spin, so we can't possibly look at this type of interaction. But we wanted to look at something that was local as a demonstration of how the simulations would work. So we chose a vector interaction in 1+1 dimensions. It had an added complication because of how left and right-handed movers move. We had to introduce the charge conjugation operator sitting here in the lepton spinner. So here we now, for each spatial site, we now have to add registers for the electron and for the neutrino, for the anti-electron and the antineutrino. So instead of having 6 + 6 per site, you now have 8 + 8. So you're looking at 16 qubits for one spatial lattice site. The Hamiltonian is straightforward to work out. One takes this 1+1 dimensional operator and then maps it onto spins through Jordan-Wigner. It's quite complicated. Well, it's not complicated. There's just a number of terms. One can choose different encodings or different mappings of qubits that for a small number of sites turns out to be useful and greatly reduces the structure of the Hamiltonian. But I won't say any more about that. It's in the paper. So the weak Hamiltonian, for instance, the beta decay will connect a down quark to an up quark and then producing in this new mapping, if you like, an electron and an antineutrino. And I've used tilde here because we've done a diagonalization to include the kinetic energy. And so then one can perform simulations of what one finds. So for beta decay, one has some isolated system. It undergoes beta decay. You expect an exponentially distributed probability. But if you only had one available quantum state for the system to decay to in a finite volume, in fact, you'll find a periodically oscillating function. You won't find the exponential that you're used to seeing for the decays of particles in 3+1 dimensions in an infinite volume. And so for this particular system, we're able to do simulations shown here on the left as to, these are classical, as to what one expects to see on the device. With one trotter step, 2 steps, and 20 steps. It's a nice oscillatory function. Whereas on the other hand, and we also then simulated what you would find as you increase the density of states, simply implementing Fermi's golden rule, and how you would actually evolve from an oscillatory function to recovering exponential decay. And of course, systematically, one can do that as you increase the density of states and you work in larger volumes. In fact, you can readily decay, you can readily extract on a quantum device, ideal quantum device, the exponential decay curve out to some time, and then of course it'll turn over. So in any simulation, you're not actually going to be able to recover the exponential lifetime or decays of unstable particles, but you will be able to find a curve as long as you had enough resources that looked exponential over some time interval and then will turn over and start oscillating again. So this is kind of interesting. So one of the questions is how do you start from a simulation with just a few available states and recover a prediction for the lifetime of that particle at infinite volume? And so this is really yet to be established. So again, there's different quantum circuits that one has to build. And so in this particular work, we had to prepare the initial state of a single baryon. We know what the wave function is. And for an L=1 system, it's particularly simple because the interpolating operator is the down, down, down. And so one only has to perform a variational quantum eigensolve for the up vacuum that tensor products with it. So actually we performed VQE to initialize the state. And then the evolution operator, which is the sum of the weak and the strong Hamiltonian, again, has an implementation via a quantum circuit that looks like this. And then after applying this for some time period, one just looks for the number of electrons that you have in your quantum register. And that tells you whether you've had a decay or not. So you look at the number of electrons and anti-electrons. And if you have signals there, then you've actually had a decay. So we were able to run this on Quantinuum's 20-qubit trapped ion quantum computer. It's a remarkable device. The simulator reproduces essentially within error bars exactly the results that you find on the device. So the simulator is H1E. So these are the brown and green points on these curves, and blue is the results from the quantum computer itself. And so you can see that these.
Sorry, another short question.
Yeah,
so
sure.
you already answered it, but the question is about the meaning of VQE.
Oh yes, right. Sorry, yes, earliest question. So the VQE algorithms, the variational quantum eigensolver. Those words only give you a rough outline of what happens. So, for instance, if you wanted to prepare the ground state of a given Hamiltonian, then one has a parameterization of your wave function on the quantum device. For small systems, you can do it exactly in terms of angles. So, for instance, if your wave function, say you have a four-state wave function that you have on 2 qubits, then there's only 3 angles that define completely that wave function. And so with that parameterization, you can choose angles, say θ1, θ2, θ3, and act with the Hamiltonian and ask what the energy of that trial wave function is. And then you can vary those parameters, θ1, θ2, θ3, depending on what you found. So for instance, you can evaluate gradients then of the Hamiltonian and vary and iteratively evolve the system to the ground state. So this is a combination of quantum computing to take matrix elements of the Hamiltonian and a wave function that, you know, asymptotically you can't perform on a classical computer. It gives you a real number, the energy, which then you can then search through Bayesian optimization, or you can do gradient descent, for instance, and then arrive at the minimum. So that's what the VQE algorithm, roughly speaking, is.
Perfect, thanks.
Sure. And so in this particular circuit, for 1 trotter step, it requires 59 entangling gates, the ZZ gates, and for 2 trotter steps, 200. And you see that by applying a circuit with 200 entangling gates on this quantum device, you actually find completely consistent results with what you would expect. The error bars are from the fact that the resources required, we could only run 200 and 400, so 200 shots on the device and 200 shots on the actual device and 400 on the simulator with the resources that were available to us. So these error bars are entirely statistical. The number of CNOTs for this is very similar to what we showed before, because the weak Hamiltonian is actually just a small contribution compared with the contribution of the Hamiltonian of the gauge field. And so you're still looking at about 3.5 million CNOTs to do the beta decay of a single baryon for 1 trotter step in 1-dimensional QCD for L equals 100. So the second topic I wanted to talk about, so I've got 5 minutes, so I'll do this. Let me try and do this a bit more quickly, if that's okay.
Yes, sure.
Okay, so one of the things that's been really focused since quantum simulation became into the nuclear community is looking at the flavor evolution of the coherent flavor evolution of systems of dense neutrinos. Such systems are found in supernova, and so this affects the transport. The evolution of the flavor of the neutrinos affects the transport, because electron neutrinos interact with matter differently to mu neutrinos or tau neutrinos. They have charge current interaction that the others don't. And so roughly speaking, this is sort of a very hand-waving cartoon that somebody else created. I didn't create it. And there's been a number of works looking at the evolution of small systems of neutrinos, 4, 6, and how they evolve, and how does the flavor evolve from some initial configuration of neutrinos moving in a cone with some interaction that's well defined by the standard model. So the Hamiltonian that one has normally to work with has 2 terms. One is the interaction with the background matter, and the vacuum. So it depends on the interaction, the vacuum oscillations, which is encoded in this vector B with a spin operator, and then a spin-spin interaction. And the important thing to keep in mind is the spin interaction. The spin is really an isospin space. So the states that you have are orientations between electron neutrinos and mu neutrinos. And as I mentioned, there's been a number of works before. The circuits are actually pretty simple, as I'll show you in a little bit. And so there's been previous works on the IBM devices looking at the evolution of neutrinos with varying degrees of success. There's been studies of dynamical phase transitions in these systems by Alessandro Ruggiero and others. There's been work on classical simulations of entanglement in these systems. We were able to perform simulations of a small system on using the D-wave annealer, using the Feynman clock algorithm to do time evolution. And there's been recent work from the University of Trento by Valentino Amatrano and collaborators looking at the systems of 4 neutrinos and looking at how, for instance, electron neutrino turns into a mu neutrino, and looking at the entanglement and so forth, the two-body entanglement. So we set about doing this on Quantinuum device with 20 qubits. We could look at much bigger systems. In fact, we have results for 20 neutrino systems, but the results I'm going to show you are for 4, 6, 8, and 12. The quantum circuits that were implement the one-body term and the two-body term, and they're quite simple to prepare with the native gates on the trapped ion system. The initial wave function we chose was chosen by everybody else in this field at the moment. There's a tensor product of half electron neutrinos, half mu neutrinos or X neutrinos. And then there's the angular, the set up in angular sheets. And so the device performed well. As I indicated before, we were able to pull off results for 4, 6, 8, 12 neutrinos. We were able to time evolve the system forward, look at the inversion probability, look at, in fact, higher order correlations in these wave functions, these systems, and we're able to look at the entangles, the multi-neutrino entanglement, which has not been done before. And so here gives you some idea of the quality of the device. The squares are these points like this. These squares are what we obtained from the H11E emulator or simulator, and the circles are what we obtained from the trapped ion quantum device H11. So you can see that the device is working well with the expectations in the systems with 8 and 12 neutrinos, and agrees again with what you'd expect from the emulator. So because it's a tensor product state initially, we're actually able to pull off the entanglement, the in-body entangle quite efficiently through the quantum circuit shown here. You prepare the initial state, half of them down, half of them up, tensor producted, evolve forward with the Hamiltonian, apply sigma y as defines the action of the entangle to some subset or all of the objects, evolve forward again with e to the IHT, and then perform measurements in the computational basis, and that was sufficient to measure the entangle. And so we're able to actually obtain non-trivial results that were they're actually very interesting. So the upper scale is linear, the lower is log, and so the red curve is for 4 neutrinos and the green curve is for 6 neutrinos. So the blue curve is the 4 tangle of the 4 neutrino system. The green curve is the 6 tangle of the 6 neutrino system. So turns out that there's actually a lot of systematics here. If you look at the entangle and define a sort of a renormalized or normalized entangle by this factor of n to the power of little n minus 2, then in fact you find these curves as a function of big N and little n converge to universal lines. I don't want to say actually universal because it depends on the parameters, but they converge as big N goes to infinity for a given entangle. So that was not known before, that you had this type of convergent behavior. And if you ask then, what does this mean? So if you were to take the neutrino system and put them together in all possible, in bell pairs in all possible ways, and ask for what is the entangle in that system, then it is less, parametrically less than the entangle that we were actually computing in the neutrino sector, which tells you that there's actually multi-neutrino entanglement beyond just 2 neutrino entanglement in these systems. And that's demonstrated in the difference between these curves. For instance, the difference between the solid and the dashed. The dashed is what we find empirically from the simulation, and the solid is what you would arrive at with 2 neutrino entanglement only. So there's a pretty nice systematic in these systems. we're pushing this now to systems of n equals 20 and trying to explore different structures, see whether we can identify exactly what to try and explore somewhat what the entanglement structure is better. The next generation simulations here are straightforward. There's a new gate on the Quantinuum that means that we can replace the sort of the most optimal 3 scene Quantinuum presently for what I showed you, but there's a new gate that's available and it looks like this. So we're actually able to use this new implementation more effectively. So the last thing, and I'm going to do this very quickly actually because I'm already over time, but I want to mention it, is work with Caroline Robin. So she's a research assistant professor at in Bielefeld. She was at the INT for a couple of years. And this is a totally different arena. This is looking at a multi-nucleon system. So for instance, if you have a large nucleus and then you have some valence space on top of it, imagine you have nucleons now where they have an energy for spin down and energy for spin up, and you have n of them. And they're interacting in such a way that where they can both scatter between states. And the effective Hamiltonian then has the form of a JZ piece for the one body. And then there's an interaction that can raise you 2 units in angular momentum space and drop you 2 units in angular momentum space after you've mapped the corresponding annihilation creation operators. And so one can then map this then onto an SU2 space on a total J basis. And in fact, if you have n particles, then you're working with a J equals n over 2 irrep of SU2. By working with effective model spaces on reduced numbers of qubits and learn the Hamiltonian in that effective space, and then do VQE simultaneously to arrive at the ground state wave function. So this is a combination of Hamiltonian learning and VQE in one unit. This was the first time we'd heard of this being done. And so the transformation here is well known. It's been applied before between the states because this model is exactly soluble, where you can map annihilation operators into different annihilation creation operators into linear combinations of other ones. And then because you then have a hierarchy in the numbers of particle hole excitations, you can perform a truncation in that basis. And so the question is, can you actually learn a Hamiltonian in the truncated space, a small dimensional space, and recover the full Hamiltonian of the wave function using effective field theory techniques and effective model space techniques, and using a quantum computer? So the method that we had then was calculate the matrix elements of a Hamiltonian that depends on a parameter beta that's not the full Hamiltonian, but truncated down, and then a variational wave function. And so we'll go to the quantum device with a Hamiltonian at some beta and wave function at some theta, evaluate the energy and evaluate derivative. On how you pack the circuits onto the chips, and then brought the results back, did a classical evaluation, in this case, gradient descent, made a new choice for theta and beta, and then sent it back to the quantum device. And so these are the results we obtained. For instance, the energy of the simulator versus the energy of the device. So this is IBM Lagos, and we use 32,000 shots. We're on 1 qubit and 2 qubit, and one sees one can recover the energies in an exponentially converging way, and one recovers the expected amplitudes well. And you can burst, for instance, from a single qubit and 2 qubit calculation in the truncated space back to the full wave function, very efficiently for the Lipkin model. And so the result, the dash curves are the exact result of the full system, in this case 30 particles. The results here with the simulator and Lagos for 1 qubit. So this is recovering the exact wave function from just 2 states. And then the blue and orange results from the simulator and IBM device with just 2 qubits. And you can see over here, the fidelity of the wave function is increasing exponentially as you converge. So, okay, so I didn't really do justice to this project. This is not in the process of being written and finished. But let me summarize. So I've given you an overview of 3 projects on digital simulation that we've been working on. One is 1+1-dimensional QCD. One is coherent neutrino evolution, relevant for supernova, and one is a nuclear mini-body system that actually seems very amenable to using effective field theory techniques and truncations and new Hamiltonian. For this work. So thank you very much.
Thank you very much, Martin, for this great and very informative talk. So this was really excellent. So let me now open the floor for questions. And I see a very good question in the chat. And the question is it possible to solve the same problems without using quantum computers?
Great question. Everything that I've shown you today, the answer is yes. There's nothing here that I showed that we can't do with classical computers. So particular 1+1 dimensional field theories, where using tensor methods, the Schwinger model has been pushed out quite far to large systems and with high precision. So at the moment, but this is not just limited to what I've shown you today. It is the case that quantum simulation has not produced a quantum advantage in any scientific application. So all of this work is really preparation to understand how our problems scale, the quantum resources that will be needed to actually do computations that will impact experiment and other areas of theory. And so this is laying groundwork, and it's educating us, developing quantum circuits and so forth. But at the moment, there's been no quantum advantage demonstrated for any scientific application.
Okay, next question from Directini. Is the decoherence renormalization algorithm a systematic procedure? Could you discuss it a bit further?
Yeah, sure. Right. So it's a well-defined procedure, but in the sense that it's also not unique, if that makes sense. So for instance, so the whole intent of that, so firstly, there's a number of things that happen. Firstly, you do the Pauli twirling and turn your coherent errors into statistical errors, which you can at least which you can mitigate those errors dramatically by just large numbers of measurements. So instead of having, say, 100 measurements, you would Pauli twirl with, say, 20 different configurations and do 2,000 or maybe 100,000 measurements or something, and you drive the error of a given circuit. That doesn't address the decoherence. You just transform coherent noise into stochastic noise. The device is decohering as you're performing measurements, and even if you leave it by itself. And so the question is, how do you so you've run a quantum circuit, how do you remove the effect of the device decohering from your circuit and from just sitting there? And so you can take your circuit and you're free to construct this any way you like, but you can imagine running your circuit forward for half the time interval and then running it backwards for half the time interval. And that applies your gates. It doesn't apply the gates throughout the entire Hilbert space if you applied for the full time, but it moves you into the Hilbert space and then moves you back. And any deviations from the initial state tells you limitations, will tell you about the decoherence of the device because you acted on it for the full time. And so you can then use what you measure from that forward-backward evolution to understand how the different states are evolving towards the classical, and then remove it using linear approximation or higher order. So far people have only done linear removal, and that's in fact why those points that I showed you were slightly below the line. Now, on the other hand, one doesn't have to go forwards and backwards. One can just go forward with, say, for instance, 0 angles, but by using barriers so the circuit doesn't collapse under transpilation or compilation. So, and that's another way to do that. And it turns out they have slightly different behaviors. They're the same with an error bars. And so we actually did both to look at the behavior of both and just picked one. So, so the procedure was basically just invented. Does it go to scale? People have used it on relatively modest systems, but the work in the papers by Sarah Powell and Randy Lewis and collaborators that I showed you, and by Christian Bauer, I mean, so you can go out to say 400 trotter steps, whereas if you don't do this, your systems has noticeable deviations after say 20. It makes a huge difference. And you can find signals where naively there are no signals. And I do have a figure. Let me see whether I can find it without. So this is something that we're in the process of preparing, but it has a figure that I. So this is a graph from, again, IBM results on a single plaquette with the color IREPs of 1, 3, 3 bar, and 8. And the raw data that comes off the device that's unmitigated for decoherence is these black points. And when you run the mitigation circuit and do this rescaling, then in fact you find these blue points. So each of these is one trotter step. And so you can see that if you look at these black points, it's very difficult to see that you have a signal in here. There's a hint of a signal. But when you perform precision decoherence renormalization after you've done Pauli twirling, that has meaning and agrees with what you'd expect. And these error bars are now increasing. These are both statistical and stochastic. So you can see how effective this is by this graph.
Yeah, that's quite impressive.
Yeah, it was quite remarkable. In fact, so Sarah Powell here, she's an undergraduate. She's applying for graduate school. So if you're looking for a great graduate student, so she actually did this as an undergraduate project, and she spent the summer with us this summer actually. And so she actually brought this technology to us.
Wonderful.
Yeah.
Okay, so while we are waiting for more questions, I also have a question. So on slide 22, you showed a very interesting result with the peak in entanglement entropy.
Oh, sorry. Okay, so
I think it was no, I don't think it's.
Let me see.
There was this transition from quark anti-quark to baryon. Yeah, this one.
Yeah, yeah.
So in this upper left slide, what was the definition of entanglement entropy? What were the subsystems, so to say? Is it between quark and the rest of the system? Is it between two spatial parts of the system? How was it defined?
Yeah, so good question. Yeah, I glanced over that. So here we're looking at the entanglement between quarks and antiquarks. So this is a system with just two sites. So we split the system just into half.
I see.
And we did the linear entanglement entropy 1 minus trace rho squared.
I see. Okay, so there are just two sides, and then it's basically entanglement between these two sides. Okay,
that's right. So there are far more extensive things to be done here. Absolutely, as you allude to. But this was just the first thing that we
did. Great. So this is very interesting.
Yeah.
Okay. Other questions? Well, I don't see any. So let me thank Martin on behalf of all of us. I think this was a really great talk, and I'm sure we all enjoyed it very much. So thank you very much, and I'll give it to the organizers.
Yeah.
Thank you.
Yeah, thank you so much. So yes, thank you all for joining. So
yeah, you are also welcome for next week's talk, which would be an experimental one about S-Phoenix. So see you next time. Thank you.
Thank you very much. Bye-bye.
Thank you. Bye.
Thank you so much.